Brilliant, thanks. So to be honest, I just came here to put my hand in the oil and to eat the pizza, but I haven't given an in-person talk in what feels like forever. I think the last one I gave was in March. Everything else has been on Zoom, so this is like surreal that we're back in like the real world in a room full of people. So we'll see how this goes. Okay, so my name's Adam. I'm a postdoctoral research fellow at the International Centre for Radio Astronomy Research over at the University of Western Australia. This talk is going to cover a few different subject areas. It's going to cover science of climate change. It's going to cover topics related to supercomputing, and I'll touch very briefly on astrophysics because that's the thing that I actually do for a living. But it's not going to be too astronomy heavy. So I'll start with, as any talk should, with the motivation and the problem at hand, which is global warming and climate change. That's all right. This plot here is showing just sort of the go-to data, which you can very easily download from the appropriate government department from the United States of America. Each of these points here is just showing the temperature change from the average between 1880 and 1930 up to the present day. So there's I think annual measurements, maybe slightly finer resolution than that. And as you can see, the temperature, this is the global surface average temperature. Is the rise is consistent with an exponential function, which is quite concerning. And we've already reached the point where we're more than a degree above pre-industrial levels. And I should also point out that in Australia, the rise in global temperature that the rise in temperature that we're experiencing is greater than the global average rise. So in Australia, it's closer to something like 2 degrees at the moment, as I understand. So as we all know, this is a problem for many reasons. Increase in temperature means melting of ice, means rising of sea levels, means mass displacement of humans, means mass extinction of species, means food shortages, etc. And so this is really, I would say that this is the biggest problem in the world, full stop, bigger than coronavirus or anything else that's been going on this year, or for the last couple of decades for that matter. And we're kind of hurtling towards this humanitarian and ecological crisis, if you like. So this is a really big concern. And we know that this is a crisis that is man-made. This plot here is from the global carbon budget. This is an annual report that comes out. If you've never checked out one of these papers and you want to learn about climate change and emissions from fossil fuels and so forth, this series of papers is really worth checking out. You're going to need to check out the most recent one, of course. So every year they basically update graphs like this, so they just add an extra point and they get another publication. Who knows how many citations they get out of it. Anyway. So here we're seeing emissions, so this is anthropogenic emissions caused by humans since 1850 as a function of time. You'll notice that the shape of this curve is very similar to the rise in temperature. And you'll notice that the bulk of the CO2 flux that is being produced comes from the burning of fossil fuels in industry. On the negative side of this y-axis, you've got observations or measurements of the actual CO2 concentration, so it's the differential of the CO2 concentration as a function of time, in the ocean, the land, and the atmosphere. So these are the three natural sinks for carbon dioxide to end up in, of course. The stuff that stays in the atmosphere is what causes global warming, right? So if you've got CO2 trapped in the atmosphere, this re-radiates energy back down to Earth that would have otherwise escaped. And the stuff that goes to the ocean is problematic as well because this increases the acidity of the ocean. This is what's killing the Great Barrier Reef and causing extinction of species in the seas. Okay, so in principle, these two things should balance out because these are, these are completely different independent measurements on the two sides of these things. And in principle, flux in should equal flux out. It's continuity of mass, essentially. And there aren't error bars here, but if there were, you'd trust that these are consistent with one another. Okay, so if you just read off the final point on the plot to get a sense of where we're at now, or rather where we were at in 2018, notice that this paper was published in 2019, which means the data that it assesses goes up until 2018. There's always a bit of a lag in analyzing these data. At the moment, the world is producing something like 42 billion tons of carbon dioxide equivalent emissions per year. And if you divide that by the entire population of the planet, this ends up with a value that's 5.5 tons per person per year. I tend not to talk about emissions in terms of like overall per person. I prefer to think of this in terms of per non-dependent, so per adult, because I think it would be ridiculous to assign responsibility to children for any carbon emissions, right? So in this case, non-dependent means people above the age of 15, simply because that's the simplest statistic that's publicly available. So this is the number I want you to keep in the back of your mind as the global context for emissions, so 7.3 tonnes per non-dependent per year. Right, so that's globally. I also want to give you some domestic context. So in Australia, our rate of emissions is a lot higher than the global average. This plot, again, is just taking government data, which you can easily access yourself. So this is from the Australian Federal Department of Industry, Science, Energy and Resources. There are two lines here. One is the total emissions as reported from 2002 all the way up to 2020, but I've also included a line here that excludes land use change, and forestry. And the reason for doing this is this is basically fossil fuel burning, okay, in the cyan line. And it might be a little bit confusing to see the total be less than something that is not the total up here, but it is possible to have to record negative emissions through land use change. You can imagine that reforestation essentially is negative emissions in that case. So that's why that happens. But this line I think is the one that's most important. When you hear government officials telling you that emissions have been falling since 2007 or whatever, they're talking about this. The actual burning of fossil fuels and the direct pumping of CO2 into the atmosphere has actually still been going up since then. It's basically flattened off now, and maybe it's starting to turn over. At any rate, the current numbers for Australia are more like 26 tonnes of emissions per person, per non-dependent per year. So that's almost 4 times the global average, which is horrendous. Many of you might be familiar with the Paris Agreement. This is, of course, an accord that's signed by many countries. The goal of this is to try to limit global warming to within 1.5 to 2 degrees Celsius by the end of this century. The thing is, in order to achieve this, emissions need to be continually and rapidly reduced from now. And when I say now, what I actually mean is yesterday. And when I say yesterday, what I actually mean is it needed to have already been happening for years. And it hasn't been. So I can demonstrate that with another plot. So again, this is global emissions with time. You only need to focus on the cyan line here. So this is a paper from 2018. It has data going up until 2017, and thereafter is basically a model or a scenario for how we might be able to change our emissions in order to keep the temperature within that sort of 2 degree threshold. Okay, so emissions as a function of time. On this side, you've got cumulative emissions here, but also this shows you how much warming that translates to. Okay, so here we are in 2020. We should have already been on the downward curve, but we're not. We're actually still on the upward curve, globally speaking. Okay, so at the time that the Paris Accord was written up, the goals were roughly, we need a 20% reduction in emissions by 2030, and then 100% reduction, literally nothing, by 2050. Given that in that time the rate of global emissions has still gone up, those targets need to be even more ambitious than that. Okay, so that's a bit scary and confronting. And this slide is intentionally blank, just to let you be somber for a moment. You can imagine that if you start having conversations with your colleagues at lunchtime about this, the question comes up, well, how are we potentially contributing to this problem without really realizing that we're doing it? And this is literally what happened between my peers and I at ICRAR. And so we wanted to actually find out, what the average emissions associated with doing astronomy is, given that that's what we're doing on a day-to-day basis. And there's so much going on behind the scenes in terms of the resources you're consuming that you often don't think about. We felt it was time that we actually calculated that. And of course, me having a loud voice meant that I was then assigned the task of figuring out what those numbers were, right? You always get, ask a question, great question, Adam, why don't you tell us the answer? Okay, so I did. So I was tasked with leading a group of people, including Sabina here, she was involved in this work, where we wanted to, so we needed to calculate what the typical emissions of an astronomer were. And in order to do this, we first needed to target relevant areas of our job that we thought would be contributing to this. Okay, and try to pick out all the things that we thought would cover the bulk of where our emissions might be coming from. So these are the 4 sources that we looked into and actually got data for. Going into this, we thought that flights might be the worst thing. As many of you might know, academics are notorious for flying all over the world all the time to go to conferences and collaborate. It's not too difficult to imagine all of the jet fuel that gets burned and the emissions that get dumped directly into the air, and those numbers can be quite large. And so we were expecting that to be the worst going into it. That turned out to not be the case. Of course, emissions associated with supercomputing offices and observatories, this all comes down to energy consumption or electricity consumption. So what matters there is what's producing the electricity that's going into the grid that's then being consumed. Right. I'm just going to dive straight into the main result of this paper, and it turned out that supercomputing was actually by far the largest contributor to our carbon footprint. It's about 60%. There's a significant error bar on that, of course, but if you just trust the fatter bars at face value, it's about 60% of our emissions. So flights was a distant second. The powering of our observatories was a close follow-up, although we could only get a lower limit on this because we only had limited data available to us. We didn't get every single observatory that astronomers use. There are lots of them. So probably this is a little bit larger than flights, but still should be, we expect, is relatively small compared to supercomputing. And then, of course, there's the powering of our offices as well as right down there in fourth. So given that this is a place where people are probably more interested in supercomputing, and given that that's the bulk of the emissions, that's just what I'm going to focus on for the purposes of this talk. So I'll tell you a little bit of the details about how we got these numbers. So these are kind of the details in a nutshell. We had data provided to us from the Pawsey Supercomputing Center. They're one of the many supercomputing centers that astronomers use. They're local. It made sense to get in contact with them. So what they actually provided to us was 18 months of their power bills, of which we only used 12 for practical reasons. So we knew exactly how much energy their entire supercomputing center used over a 12-month period. We also knew what fraction of their resources are dedicated to astronomy. Okay, and we also know the number of CPU hours that were consumed by astronomy at Pawsey over that same period. So this allowed us to estimate what the energy per core, including all overheads, was. Okay, so 53 watts per core. That was the number that we went off. And from this we extrapolated. Okay, so we know, roughly speaking, and this is very much an approximate number, that for the entire field of astronomy within Australia, our requirements are something like 400 million CPU hours per year. This is to cover all the processing of our data, the running of our simulations, etc. It's quite a computationally intensive field. And we also know from Australian government figures what the emissions produced per kilowatt hour are for every state and territory in the country. And when you do a weighted average over those states, you end up with a number that's about 0.72 kilograms of CO2 per kilowatt hour consumed. So just to back up some of those things that I was saying, this is a slide that sort of comprises some of the main information from Pawsey's annual report. So you'll see that radio astronomy, as I was saying, astronomy uses about 25%. That's actually all just radio astronomy. So it's just one subfield of astronomy that uses 25% of their resources on an annual basis. In that case, it was about 51 million CPU hours over that period. So these are the values that allowed us to actually make that 53 watts per core calculation. Of course, there's also optical astronomy, UV astronomy, X-ray astronomy, every part of the electromagnetic spectrum astronomy. But most importantly, there's theory and simulations, which is the field that I work in. I'm completely reliant on simulations like this. So this is a cosmological hydrodynamic simulation. It's one of the state-of-the-art ones. What we need to do as astrophysicists, or in my case as an extragalactic astrophysicist, there's a mouthful, is we simulate whole regions of the universe from the dawn of time, literally from the dawn of time until now. And within those simulations, we try to form tens of thousands and sometimes even hundreds of thousands of galaxies. Just describing the laws of physics that are relevant for that's complex enough. Solving them is obviously far more complex. There are models going on a single particle level within inside. So this simulation will have tens of billions of particles in it. And for every single one of those particles, there's an entire array of models to describe how that particle interacts, and not just with other particles, but with itself. So this is incredibly complex. Okay, so in this simulation, you can see all of these lovely galaxies, these forming and evolving. Of course, we only make these videos for talks. We don't actually use them for science. Okay, so now that I've distracted you with that looked really good on the screen, by the way. I love it. Again, going into the the details a little bit further. So from that 400 million CPU hours that I said is roughly what we use in a year, we know how this is broken into different places across the world. So about 40% of our compute requirements are actually covered from overseas facilities. Astronomers are obviously very international in terms of who they collaborate with. A lot of the time, you're anchored to where your data are for where you do your computing. For me, that's the case. A lot of my computing is actually done on a machine in Germany because the simulation that I work with is there. And it's too much of a hassle to transfer the petabytes of data over to here. It would be redundant and a waste of resources to do so. About 10% of our requirements are covered by the AUSTAR supercomputer. This is at Swinburne University of Technology in Melbourne. 20% of our requirements are covered in Western Australia. This has historically, of course, been not entirely, but mostly Pawsey, but more recently we've now been working with Doug, or at least many people within the department have been working with Doug, which is really cool. And then about 30% are covered mostly by the national computing infrastructure in the ACT, but I put /New South Wales here because when you look at government figures on the electricity grid, the New South Wales and the ACT are kind of lumped into one. And of course, there are many more astronomers. Well, actually, I think there are more astronomers in New South Wales than there are in the ACT. You might want to fact check me on that. It doesn't really matter. Okay, so that's just in terms of the compute time. If you actually translate that into emissions, the donut chart changes a bit. So I might just flick back and forth so you get a sense for this. Okay, so WA's 20%, stays about 20%, but Victoria and ACT/New South Wales go up and overseas goes down. And this is simply because energy in other countries is greener than it is in Australia, right? So this number is based just on what the OECD average is for emissions per kilowatt hour, because it's very complicated to track every supercomputer or high-performance computing center that we use across the world. There's just too many. Even just to get the list of countries that are involved would be a task, let alone the cities, let alone the actual facilities. So there's a significant error bar on that, but the other ones we can be relatively confident about if we trust the government figures, although they don't give error bars. So, nevertheless, I'm digressing. So Victoria has the highest emissions per kilowatt hour that goes into the grid of the states that were relevant for our work, and WA was actually the lowest, which is nice to know. It's still quite high, but it's lower than the eastern states, just due in part to how many solar panels there are on roofs in WA, which is cool. Okay, so I'm going to come back to this plot again in a bit, but just to kind of summarize the full results of this paper, if you actually sum up the supercomputing, the flights, the observatories, and the offices, the job of being an astronomer for a full-time equivalent staff member produces 37 tons of CO2 equivalent emissions per year. This is 40% more than what the average Australian does in their work and their home life and from their children, etc. combined. And it's 5 times what the global average is for all of that. So something needs to be done about this. So this paper was actually originally written for a mid-decadal review that we have in astronomy. So every 10 years we come up with a decadal plan about where the field is going, and halfway through each decade we have a review on whether we're actually headed in the right direction and what things have changed, because in 5 years of research, a lot of things can change. So like, for example, when the last review was written, there was nothing about gravitational waves in there because they hadn't been discovered yet, right? And you can imagine that's a major thing. So we do these reviews for many reasons, and I think this was the first time that there was a sustainability section devoted, which is what I was in charge of. But once that was put out into the public domain, I got an email from the editor of Nature Astronomy saying, hey, love your article, would be great if you wanted to submit it and have it refereed and published in our journal, which is pretty cool because they're obviously a pretty big journal. And the conversation that got started there has led to a whole bunch of further interaction with other people around the world. And what's been really nice is that they actually invited a whole bunch of companion pieces to go with this, and they sort of centered the issue around it. Now, unfortunately, when you're talking about emissions in astronomy, you don't really have any good graphics, so you don't make the cover of the journal. But hey, the detection of phosphine in Venus didn't make the cover of the journal either, so that's fine. Okay, so there were 6 companion pieces written alongside, sorry, 6 pieces including ours, plus an editorial in this. And I'd recommend checking it out. Most of the papers are only like 3 pages long and they're pretty easy to digest. Rodrigo's read them. He's not an astronomer. He knows quite a bit about astronomy though, to be fair. Sorry, just to put you out there, Rodrigo. Okay, so one of the the papers, one of the companion papers that was written was by a team at the Max Planck Institute for Astronomy in Germany. They did a very similar study to what we did, just looking at calculating the total emissions of the staff members at their institute. So this is quite a big institute, to be fair. So even though it's only one institute, there's plenty of people going into this. You'll see that there's a pretty big discrepancy between what's going on in Australia and what's happening at the MPIA in terms of emissions being produced. And this is, as far as we can tell, this has nothing to do with the requirements of the job. There's no reason to think that what an astronomer does in Germany is any more than what an astronomer does in Australia, or at least in terms of the resources that are required to do that job. So the major discrepancy here is, at least from the electricity standpoint, which is where supercomputing has been lumped into, is just the fact that the energy is a lot greener in Germany. There's a much higher fraction of renewables there. So for them, flights was worse. Although there's a caveat to this, and I don't want to go on too much of a tangent, but it's maybe a point of interest. So they doubled the number that we put in our paper and for flight emissions, and there's validity to this because there's actually a significant systematic uncertainty on how much global warming comes from emissions from aeroplanes, because they're not emitted at ground level, right? If they're emitted at ground level, you'd know that the science for that is relatively straightforward. But when they're emitted at altitude and they start producing things like contrails, the same mass of CO2 can actually have a greater global warming effect. Okay, so, and the uncertainty on that global warming effect is literally like a factor of 2 or 3. So doubling that value is actually fair. Okay, so that was just one of the companion papers. One of the other ones actually looked at coding practices. This is a very busy plot. You don't need to digest all of it. I've just shown it because it's the only plot in the paper, really. So this was looking at how coding practices can have an ecological impact. So these pinkish/magenta points along here are basically just like a bunch of typical tasks that an astronomer might want to do. They've been idealized for the sake of the argument that they're trying to make. Sorry, this is solution to a task versus CO2 production. So those points lie along a line because it's just a simple case of if you're running if you're trying to solve a problem in like a single core manner, I suppose, the emissions that you produce is just proportional to the time that it takes. But if you choose the wrong language, you might shift the line on which those points would exist. So that's what the magenta arrow is trying to highlight. So if you pick a higher level language that has more overheads, you'll just produce more emissions. That's kind of obvious. The thing that wasn't obvious to me, which I certainly learned about, was the fact that multi-core processing is a lot more carbon intensive for a fixed task than single core processing is. So let's say you've got a task that you want to complete and you're going to complete it with one core. You know it's going to take you, 10 to the 4 days to complete. That's far too long. That's not practical, is it? But it's only going to produce 10 kilograms of CO2, which is not so bad. But if you parallelize the specific task, I can't remember what the details of the task were. It doesn't really matter for the purposes of this exercise. If you run that on 1 million cores instead, okay, sure, you complete it in a tenth of a day, but you're now producing 10,000 times the amount of CO2 you did before. And just to be clear, that's not 10,000 times the amount of CO2 per unit time. That's 10,000 times the amount of CO2 total once the task is complete. Also, some interesting things that they touch on is the fact that if the faster your processor is, again, the more energy you will emit for a fixed the more energy you'll need for a fixed task. So then, of course, the more emissions you'll produce. And that if you're using a machine with virtual cores, it's going to cost more than it does for physical cores. All of that was quite interesting. I'm obviously not an expert in all of these things, but I just thought they were worth touching on and might be relevant for you guys. You guys might even be able to explain to me why some of this is the case. I don't know. So coming back to this plot, I said I'd come back to it. So just remembering that's the distribution of our emissions over different places, but that's how it was when we wrote the paper. And we wrote the paper a year ago, and it had data up until more than a year ago, because that's how publications work. Since then, there's been a change. Okay? Since then, we're no longer worried about what's happening in Victoria and in the ACT. And the reasons for this is Swinburne University of Technology, which hosts the AusStar supercomputer, which is where all of our Victorian supercomputing is done, has signed a procurement deal. They basically purchased a wind farm to power their entire campus. That's the long and the short of it. So all of their energy is renewable now, which means that supercomputer is now green, which, if you're familiar with Swinburne, is funny because their previous supercomputer used to be called Green, which wasn't green, but now their new one is. Anyway, in the ACT, it's a similar story. I actually think the entire territory produces more renewable energy than energy it consumes. So everything that's at ANU and national computing infrastructure is covered by renewable energy. So we're actually not worried about using time on NCI from an environmental perspective either. So the challenges where we practically need to focus on is here in WA and overseas. Now, of course, overseas is tricky because it's split across so many different places. I think probably the strategy there is just to be picky if we can, but the caveat there is that you're often anchored to wherever your data are, unfortunately. It's hard to have an influence there. Where we can, of course, have an influence is here in Western Australia. One of the things that would be really great to come out of coming over here and giving this presentation is seeding a plan for getting to the point where we can have, all supercomputing requirements in the state covered by renewable energy. And I think the model that Swinburne has adopted for just like wholesale purchasing a wind farm is probably a good approach. So I touched on coding efficiency before as well. That can be part of the solution, but it's never going to be the full solution. Increasing your efficiency, you can cut your emissions in half, you can cut them in a quarter, but you're never going to get them to zero. The only way you're going to get them to zero is with renewable energy. Okay, so that was the plot before. That's what it is now with the renewables as of 2020, which is great. That's what it is with grounded flights and COVID-19. Cool, that problem's been solved for us. A blessing in disguise, perhaps. And if we can get to the point where all of our our energy requirements are covered by renewables, it doesn't just have to be supercomputing, it can be everything else, we can make this entire plot blank, which would be like the dream, if you like. An achievable dream, I should say. Okay, so in wrapping up, I just wanted to highlight that I'm a member of this group called Astronomers for Planet Earth, no prizes for guessing why. I just wanted to quickly advertise that they have a YouTube channel with webinars on a lot of this stuff. So they've got some on the actual science of climate change and how climate change affects astronomy and how astronomers affect climate change and so forth, which is quite cool. They also have a website. Apparently you can have URLs with .earth now. Didn't know that. And that's it. And I'd just like to end by saying, let's act, because I think we can. And we can make a positive difference.